You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast, and I have Matt Weber. He's a professor in the Department of Chemical and Biomolecular Engineering at Notre Dame. So he's part of the Weber Lab, named after his namesake, and we're going to be talking about the supramolecular chemistry. We'll get into that. So, Matt, thanks for coming.
Yeah, no, happy to be here. Thank you for having me. It's a pleasure to speak with you, and scientists love to talk about our work, and so I love the opportunity to do that.
Yeah, so what is supramolecular chemistry? How does the chemistry you do different from, normal chemistry, if there is such a thing?
Yeah, so I think conventional chemistry as it's understood, and maybe, what people are most familiar with from, basic chemistry classes maybe they took in college or something like that would be the chemistry of covalent bonds, right? So things like carbon-carbon bonds, carbon-nitrogen bonds, carbon-oxygen bonds, chemistry that holds molecules together. When we think about supramolecular chemistry, we think about non-covalent interactions. So interactions that are individually weaker, but if you design the molecules in such a way, you can actually get really, you can kind of get ensembles of these interactions that produce a very strong overall product, right? So you can have two molecules that interact through non-covalent interactions. Maybe it's opposing charges. Maybe it's polar type groups interacting. Maybe it's hydrogen bonding, the sharing of a hydrogen atom or something like that, which can give rise to really interesting structures that can be very stable and organized on a molecular scale. And so that's sort of what we think about. We think about how we can design molecules to interact non-covalently in a very defined and predictable way.
What about like proteins and enzymes and
Yeah, sure. So I
fitting
think,
into complicated like 3D structures, molecules inserting into another.
So that's a perfect example, right? So I think proteins are, a lot of the interactions that hold proteins together are things like beta sheets and alpha helices and other sorts of non-covalent interactions, typically driven by hydrogen bonding, right? So these give proteins a lot of their structure, so-called secondary structure of proteins. The primary structure being all of the different amino acids held together by covalent bonds, the secondary structure then arising from secondary interactions.
So what kind of specific applications are you working on and trying to figure out?
We're interested kind of in a lot of different things. So we're fundamentally interested in how we can use these interactions to build systems that maybe resemble or recreate the living world, right? And so in nature, there's things such as, very defined nanoscale architectures. Right? You look at viruses and they have perfect symmetry. They have the exact number of components that is needed in order to make up that structure is perfectly defined. It's discrete. And so we're interested in, can we build synthetic systems where we can engineer interactions among these synthetic building blocks in such a way to sort of gain control over structure of a resulting assembly. And then simultaneously, we're also interested in how nature does recognition. And so, for example, our body, its immune system, part of the function of that is based on antibodies and their recognition of specific markers or antigens in the body. And so what we want to do is try to build synthetic systems that maybe recreate that type of affinity in a non-biological way. So we typically like to think in the context in this of host-guest chemistry. So a macrocyclic host, you can think about like a basket-shaped molecule. And then it has some sort of specificity in recognizing and binding to something that fits really nicely into that basket.
How would that sensing go on, though, from non-living molecules?
So it depends on how we design the molecule. So if we design the interactions in such a way, right, we can basically make these things orthogonal to other sorts of interactions that might occur, right? And so we use a macrocycle in my lab that binds with very, very high affinity to a small subset of guests. And so the thinking being that if we take this macrocycle and we combine it with one of these guests, it doesn't really matter what else is around because nothing really can compete for binding. And so we're able to actually facilitate recognition just on the basis of having such tight binding between these things, like the host and the guest that we've chosen for that application.
So you're also trying to create, it sounds like, functional groups against, you can control the chemistry of various interactions. I've read about, an acetyl group, hydroxy radical, things like that. What kind of functional groups, if that's even the right word, are you trying to create in the lab? Or what kind of functions will they have?
I think I should preface this by saying I'm not a trained chemist, right? I am an engineer. And so I learned chemistry from YouTube. I tell people it's kind of, somewhat joking, but mostly true. So we use just enough chemistry to build interesting functional systems. And so we're trying to design applications around, or functional systems around, supramolecular motifs. And so if we take, say, a host and a guest, and we want them to interact and bind, maybe we want to use that to create a modular material, right? So maybe we have a material that has a bunch of these hosts on it, and I say, I want to go and develop a therapy for X. Well, I can then take some drug or some bioactive signal, link it to a guest, and now I can load it up on my material, right? And if I decide I want to go and develop a therapy or a diagnostic test or something else for some other indication, well, I've got this modular system. Now all I need to do is take that new drug or that new bioactive molecule and attach it to the guest, and it just kind of plugs right into the macrocycle on my material, right? And so that's sort of what we're thinking about, is how we can engineer these interactions in such a way that we can build functional systems.
Well, if your chemistry is not the main thing, what of your background and credentials gives you like a unique ability to work on this stuff?
I come from a sort of interesting training in sort of crossing disciplines of chemistry, material science, biomedical engineering. I've trained in the areas of regenerative medicine and drug delivery, sort of at that intersection where those things might intersect with rationally designed materials and new material chemistry. And so that's sort of what we're able to do is, I think, maybe we're in some ways jacks of all trades, master of none, right? We capture aspects of the chemistry and the materials, but then we're able to think about creative new applications for this. So maybe it's identifying a need in diabetes, right? So a large portion of my research program is geared into improving the way that insulin and glucagon and other therapeutic molecules for diabetes function in terms of controlling blood glucose, right? And so we're able to think about materials and molecular scale interactions that might promote enhanced therapy, might stabilize the protein, might make them, more inclined to be active at high glucose, not active at low glucose, for example, in the case of insulin. And so I think it's really just sort of, we're able to kind of, use a little bit of various disciplines, piece all of this together in kind of a convergent way to think about new solutions for problems. I'm ultimately an engineer. I like to solve problems.
Yeah, no, it makes sense. What have you gleaned in studying the chemistry of this all? Like you said, we don't quite know how, a basket-shaped molecule that would be the receptacle, links up with another molecule that would, bind with it in a specific way. Like, are there any insights into how that kind of thing happens?
Yeah, I think that, some of these molecules have very mysterious properties, right? And so certainly there's obviously, the thermodynamics of these interactions are very important, right? The entropy that is often gained by, frustrated water molecules no longer having to be surrounding a hydrophobic guest or stuck in the portal of a macrocycle, right? These end up driving these interactions in a lot of ways. And then there's additional enthalpic components of this. There is, electrostatic interactions with some of these macrocycles that are increasingly appreciated and leveraged, right? And so we kind of dial in a lot of these tricks and making really good motifs, right? We make motifs that maximize the disorder of the solvent water molecules, and then also in some ways maximize or leverage electrostatic interactions to further stabilize the complex.
When you have two molecules that are going to bind in solution, do you believe it's just Brownian motion, just random motion that will align the right functional parts of each fast enough for a reaction to occur? Like, does the speed of a reaction and the completion percentage of it correlate with random fluctuations of moving molecules, or do you think there's something else?
Probably not Brownian motion, but these things approach kind of a diffusion governed interaction, right? So you can look at studies on some of these molecules that we work with, and they suggest that you have K-on, interaction, the on rate of interaction approaching the diffusion limit. So something that looks a lot like, a diffusion limited interaction between small molecules. Their K-ons start to approach those sort of thresholds for diffusion governed interactions. And so that's, I tend to think about it. I mean, there is some, these macrocycles, maybe they have some breathing modes, maybe they open and they close and they just a little bit, and there's some fluctuations there that maybe slow things ever so slightly, but it's not significant, right? There's not a massive energy barrier to complex formation with the macrocycles that we like to play with, and that's why we're able to do recognition very fast, reach equilibrium, effectively instantly with these types of systems, and then also be able to do recognition and binding in the body, right? Even in blood and flowing bodily fluids, we're able to get these systems to recognize each other, and so that's due in part to how fast the reactions occur and then how stable the overall complex is.
What's the speed of various reactions? What's the order of magnitude of the speed of a reaction typically?
We've done back of the envelope calculations of some of the systems we've worked with, and you'd be safe to say on the order of about 10 to the 7th to 10 to the 8th per mole per second. So like I said, right around that, the diffusion limited interaction is about 10 to the 8th to 10 to the 10th, somewhere in that range, depending on size of the molecules diffusing and whatever else, right? And so it's approaching that. I mean, it's you think about this, I like to kind of joke that this is kind of like supramolecular click chemistry that we're doing. We're doing recognition of molecules in a way that is mostly orthogonal, but it happens very quickly, right? So some of the best click reactions out there, some of the things that are being tried for bioorthogonal click chemistry, their reaction rates are, 4 to 7 orders of magnitude slower in terms of K-on, because you have to, you're breaking covalent bonds, you're making new covalent bonds, you're rearranging, you're doing some other things that require decent energy input. By comparison, the non-covalent recognition we're able to achieve, for the most part, is going to happen a lot faster.
Well, when you say faster, how much faster? An order of magnitude or multiple?
I think it's about 4 to 7 orders of magnitude faster, depending on which reactions you want to compare it to. But if you want to compare this to kind of bioorthogonal click reactions, alkyne, azide type reactions, these kinds of things, about 4 to 7 orders of magnitude faster.
You said that a lot of the molecules will have, it's a low threshold to reaction. So would that mean that the reaction is almost reversible, typically with the ones you work with? And if so, how do you keep products without going back to reactants in large numbers?
So in principle, they are reversible. So then it's the time scale over which these things are dynamic. And so in some sense, we control that by the affinity of the motif, right? So we use some of our favorite motifs, some of the ones we've had success with in terms of homing drugs to, tumor sites or other sorts of things like that, interact on the order of about 10 to the 12th inverse molar, if you think about that in terms of the equilibrium binding constant, or the Ka. 10 to the 12th inverse molar. I just told you K-on is maybe 10 to the 8th per mole per second, something like that. That means my K-off now is about 10 to the minus 4th per second, right? And if we just do a back of the envelope kind of calculation. And so they are dynamic interactions, but at those affinity regimes, it's approaching something that's very slowly reversible and almost even irreversible, right? You're waiting 10,000 seconds for these things to separate on average. So it's, they're very stable, long-lived interactions once formed when you're in that kind of affinity regime.
Well, is there any are there any helpers you could add to it, make sure that will prevent reactions from reversing, or will make them complete, not just faster? I know that's a catalyst, but complete more fully. Have you learned
I'd
anything
almost like
about
to go the
secret?
other way. To be perfectly honest with you, I mean, we think about this in the context of biomedical devices, right? And so we know, like, I could make a gel that I inject near a site of your tumor, right? And we could use a drug that we modify with a guest that binds at, say, 10 to the 12th inverse molar with my host that's on the gel. And so by doing that and having that kind of affinity, I can get a lot of that drug to actually home to the site of your tumor, right? But then those sites are so slowly exchanging that the drug molecule doesn't really ever come off. And so in order to make that drug active at the site, then we have to start putting in things like hydrolyzable linkages between the drug and the guest to make it, fall off and be active at the site where we care about. So I'd almost like to even accelerate that off. I'd like to take advantage of the affinity on and then come up with ways to either accelerate the off or kind of regenerate those sites so we could drug them again in the future, right? Because if I have to wait 10,000 seconds for a site to become available so I can redrug it, that's pretty slow. And the chances of ever refilling that site are very low, right? So the idea would be if we could take advantage of the affinity to home, but then if we could make that site become more readily available, maybe we could think about ways of redrugging the site.
So have you found any macroscopic principles that weren't known to you before you started this work? Any?
Yeah, we do some work actually. Speaking of macroscopic, we've been doing some things in the area of hydrogels, right? And so this is sort of some fundamental work. We can use host guest recognition as a non-covalent physical cross-linker of hydrogels. And so by doing this, we can make networks that exist, 3D kind of percolated mesh type architectures that exist with these junction points being the host and the guest interaction, right? And the affinity and then thereby the dynamics of those interactions actually can change the bulk mechanical properties. And so we've had materials that can dissipate stress over 5 or 6 orders of magnitude that we've demonstrated now. We make things that are now shear thinning, self-healing. So you could have a gel and you could push it through a syringe and then it's a gel again once it leaves the syringe, but it's able to flow under the pressure of that syringe, kind of shear thin. We're now actually even thinking about some shear thickening materials. You could think about like, making gels that could have, resistance to being cut or to like projectile or different things like that, just based on playing with these interactions and the dynamics of the interactions. So this is something I think we're very excited about, kind of from a fundamental perspective of using molecular scale interactions to drive bulk mechanical properties in soft materials.
Yeah, how would you make a substance that heals itself after it undergoes, shearing or projectile or whatever it is, or tearing?
Well, it's kind of inherent in some of these materials because we're not using covalent bonds to form the network, right? I have a polymer with a bunch of guests on it and another polymer with a bunch of hosts on it, and I mix them one to one. The hosts and the guests find each other, and now I've got a cross-linked network. But I expose that to shear, we break enough of those host-guest interactions for the material to flow. But as soon as I, reduce the shear rate, well, now all of a sudden those things can go back and find each other, and your network is basically restored, right? Versus if I had a covalent bond and I broke that in the course of some sort of mechanical perturbation, those bonds never come back, right? So this sort of shear thinning, self-healing property is kind of interesting.
So if you have 2 types of bonds, one stronger, the covalent ones, and then a material is under shear or some kind of force, the ones that are preferentially break first are the weaker bonds. And then when the material is not subject to the stress, it quote unquote heals, or the weaker bonds come back together.
Yeah, exactly. Yeah, so that's something we can play with in the, in terms of bulk material properties. We can make things that have, interesting flow properties and healing properties. So.
Yeah, that's interesting because then I guess you would think the material has a memory, but really what it does is it has 2 levels of structure based on the different bond strengths. And I guess you could engineer in more levels of structure.
Yeah, we're thinking about some things where we can play with, multiple different motifs in a single material and, get 2 different kinds of dynamic properties and other sorts of stuff. This is certainly things that we mess around with a lot. So,
are there any materials you run across that are like origami in nature, or they're so complex that they've somehow come together to adapt to all different kinds of stresses in different ways and yet still maintain their integrity?
These are things I think this is kind of an area that we're very interested in, is using these interactions to drive, hierarchical organization or structure or things like that. I can't say we're there yet, but, right now we're dangling these off the end of polymers and using that interaction to build materials. I think that's a good first step. But certainly, the kinds of interactions we're using look a lot like the other kinds of interactions that nature builds really large structures out of, right? And so if we could come up with a way to kind of program these or template them in a spatially defined way, you could almost imagine turning these into little Lego bricks or something that you could kind of, build and assemble. Very interesting and spatially defined architectures from. I think that's certainly something we talk a lot about. We haven't gone too far down those paths yet, but maybe next year.
Any surprises in what you're studying? Things that really made you scratch your head or change how you look at the chemistry?
I'd written some reviews and some perspectives in this space a few years ago, and I wrote something along the lines of, supermolecular interactions are really great for building soft materials because you can make them self-healing. And so one of the funny things is we found is if we make the interactions too strong, we can kind of lose the self-healing capacity of these materials over short times. They're ultimately still self-healing. You just have to wait a really, really long time, right? So if I have a very strong interaction, the dynamics are so slow that when I break those interactions to induce flow, it doesn't immediately come back because there's not enough, available sites to restore and heal defects because of the flow dynamics. And so that was kind of surprising to us initially, but then, as we kind of thought about it a little bit more, it really kind of made sense, right? We have very slow interactions. Healing should require available sites for new bonds to form. And we just have to wait a while, instead of waiting 5 seconds. Now we're at such high affinity interactions. Now we maybe have to wait, a month, right? And so this is sort of a different way to think about it.
So I would guess you'd be able to make carriers for other molecules, one that has, a hard backbone, I would call it, and then it has another series of bonds that can create, spaces for another molecule to be inside of it. Let's say you make like a carrier molecule and, with another molecule inside of it, and then it gets injected into the body, and then because of the pH of the heat, the soft bonds break and release what's inside, and then it reforms.
Yeah, we've thought about, I think this is sort of, more broadly thinking about this in the context of like stimuli responsive drug delivery. So if we could program these interactions to be under direction of a particular stimulus. And so one of the areas I've been interested in for the last few years is the glucose stimulus. So thinking about interactions or, stuff that could exist dependent on some sort of glucose trigger, right? And so if I were to want to design a better insulin delivery strategy, I could make something that, if it sees elevated glucose, now the material opens or swells or does some other sort of thing to release a bunch of insulin. We've called this approach in literature for the last few years kind of the fully synthetic pancreas idea. The idea that we could make, a polymer or a material that could do the glucose sensing and insulin secreting function of a healthy pancreas to sort of recreate that endocrine function of in diseased state.
Okay. So with any very specific projects you're working on that would be interesting to talk about, one or two of them, or are you not able to say like specific applications you're working on?
We're doing a few different things. I'm excited about a lot of different stuff. The blessing and the curse of my current position is I get, I have resources and people and everybody has good energy and excitement and enthusiasm, and so then we go and we try to do a lot of different crazy stuff. Right now, one of our primary efforts is in making glucose responsive and or rescue glucagon. So glucagon is the hormone that acts sort of opposite to insulin. So if your blood glucose goes too low, glucagon is secreted to make your glucose go back to a normal level. In diabetic individuals, these often there's a lot of fear and risk associated with your blood glucose going too low, and so we've been thinking about ways of making kind of glucose activatable glucagons to try to raise blood glucose back to a normal level. And so this is some work that has been funded by a few different people over the years. The Helmsley Charitable Trust and then the American Diabetes Association funded different components of this work. And so we're very excited about this idea of thinking about kind of an insurance policy for diabetics through smarter materials or smarter formulations or smarter protein modifications or tags or triggers.
So what are some of the things that can selectively change a molecule? I would guess temperature, pH, shear force. What about magnetism, electric fields? What are the different things that can modulate a molecule?
Yeah, I think you named a lot of the really good ones. We've written about different things over the years of, pH responsive, temperature responsive, salt osmotic kind of content responsive, any sort of field, magnetic, electric, all these things. We're thinking about sort of modulating properties in certain ways, playing some of these tricks. But, if I make a molecule that can bind glucose, well, maybe now I can have a different property from of the molecule when it's bound to glucose versus when it's free from glucose, for example. And so we demonstrated this a few years ago in a paper on glucose responsive insulin, where we put these little glucose binding chemical moieties on the insulin, and the insulin was more potent and more active at high glucose and less potent and less active at low glucose. And so this could be kind of like a little switch on your insulin protein to tune its potency as a function of glucose, right? And so that's one we've been thinking about a lot. I think anytime you think about cancer or addressing inflammatory diseases or other sorts of things, biomarkers specific to the disease site are really nice for kind of spatial control of therapeutic deployment. So maybe it's enzymes, maybe it's reactive oxygen species. These are obviously very useful, to kind of think about getting some sort of spatial definition in how your therapy is deployed. So those are some other ones in addition to the ones you mentioned, I think that we're interested in.
And I guess you've seen molecules wherein another molecule binds to a certain site, it changes the whole nature of that molecule. Maybe it opens up more active sites, shuts down others.
Yeah, I think that's sort of the eventual vision will be something like that, right? Where, collagen in the body, for example, is very famous for having these cryptic sites where something binds to collagen or an enzyme acts on collagen in some way, and it reveals concealed sites to reveal new bioactivity in the collagen protein that was otherwise concealed, right? And so that's sort of a vision I have or a dream I have to make, kind of sensing and dynamically restructuring materials that can kind of behave in that way, where you can have, something that comes in and acts as a trigger or an activator that then reveals new, otherwise hidden bioactivities.
And that exists in nature quite a bit.
I think the famous one that I always like is, if I'm going to cite it in a review or something, is the cryptic sites in collagen. These sites that are known to exist but are kind of sequestered and hidden until something comes in and activates them.
So how does that happen, that activation? Does the molecule twist and turn and come open, or do the bond strengths change and now all of a sudden, I don't know, the distribution of the electrons and some of the atoms change? How does it happen?
You could think about it in a few different ways, right? You could think about a molecule with a hinge-like structure that then, as it binds to something, this hinge group opens and maybe reveals something that's kind of trapped in the hinge otherwise. You can always think about, you could have molecules that have enzyme-sensitive bonds. So, an esterase or, something like that could come in and chew on a portion of the molecule and reveal some hidden activity that was otherwise sort of concealed by a steric blocking group. So you could think about, I think, a couple of different ways of doing that. Maybe it's, degradation-based, maybe it's molecular, kind of conformation or reconfiguration.
Okay. Well, very good. So what would be a great result for you in the next few years? What would you love to have happen?
I think I'd like to kind of see where we can push these materials into some new spaces. I mentioned, I'm an engineer. I do want to solve, big important problems. We've kind of bit off a big part of our research program going after diabetes in different ways. And so that's one that I'm very interested in. I think it's a very, very challenging problem. And then I look at, the landscape and the fact that 1 in 3 Americans are going to have diabetes by 2050, right? This is just an enormous challenge moving forward. I'm presently interested in kind of combating drug abuse. So thinking about, new alternatives or maybe new ways of managing pain or new ways combating addiction. I'm located in the Midwest, and we have a lot of, even a disproportionately high number of, overdoses of things like fentanyl and these other scary drugs that are very dangerous and are causing a lot of pain and suffering and early death, right? And so I'm interested in that as a problem. It's something we haven't necessarily started too much in my group on this yet, but it's just sort of it's a problem that I've circled sort of in my mind of one I'd like to think about addressing moving forward.
Okay, very good. Well, Matt, what's the best way for people to get in touch and ask questions and see papers and pictures and things like that? Most academics, I have a decent online presence, and so they can find me through the internet. WeberLab.com, WEBBER lab.com is my main website where I post our papers and things. I'm pretty active on Twitter as well, at WeberLab, if they'd like to, follow me or, just kind of keep up with the work we're doing. And then, of course, I'm pretty responsive via email. So if somebody'd like to, know more about our work or, or have, further discussion, they're welcome to try to email me. And that's, the email address is available on the website. It's just mweber@nd.edu. So, okay.
Yeah, that'd be great. I'd love to talk more. So.
Okay, Matt. Well, thank you for coming. I appreciate it.
Yeah, no, thank you for having me. It's been fun talking. So.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.